All right, everyone. Welcome back. Hopefully, everyone can hear me. Don't want to have what happened to that guy in Singapore happen to me. So let's get started. So welcome back, Experiment 6. I know you guys just had a quiz on Monday. Hopefully, everyone felt good about it. Grading is actually almost done, so it should be released pretty soon. Hopefully by maybe tonight or tomorrow. Then regrades will be open. You can submit regrades if you had any questions about your grade. So the agenda today, just remember that the experiment 2 lab report is due on Grayscope before midnight, so please submit it by 11:59 p.m. Remember, if you don't submit it by that time, I'm going to check the submission time, and if it's passed tonight at 11:59 p.m., I will have to deduct points. I don't want to do that. So remember, if it's late, there's going to be some deduction. If it's like a few minutes late, I can let that slide. But if it's like hours late until like less than 24 hours, there will be some point deduction. So let's try to get our lab reports on time. Mostly everyone has been doing that. So kudos and good job. So yeah. So today we're talking about experiment 6. The synthesis of dibenzalacetone, a mixed aldol condensation. So you, everyone probably talked about this in lecture with Dr. Levins. It's a fairly complex mechanism, kind of weird chemistry, but a very important reaction because we now have a technique to form directly a direct CC bond between two ketone or aldehyde groups. Okay, so are there any questions before I delve into this topic? Any general questions? Just FYI, all your lab reports to date have been graded. They just haven't been released to you yet because some of the other TAs are still grading. But if you want to know your score, you can always email me or something, and I could tell you, but I can't show you your actual result yet. But just know that your lab reports are graded on a weekly basis. Try not to fall behind. I learned that the hard way. So, okay. So let's talk about experiment 6. So in this experiment, you're going to be learning about, why a certain reaction occurs and why some others don't. So we're going to talk about competition between enolate chemistry and hemiacetal chemistry, mixed aldol, and the role of the reagents. What do each reagent do? The stability of conjugation. So we're going to talk about how that plays a role in this chemistry. And then the purification process, we're going to talk about a new technique you probably haven't learned, but a very important one, especially in inorganic and some areas of organic chemistry. So the main highlight today is nucleophilic acyl addition. That's where the enolate chemistry and hemiacetal chemistry comes into play. You probably heard a lot about nucleophilic acyl addition when you talk about reactions of aldehydes and ketones. So we're going to go a little bit deeper about this mechanism. Okay. So let's talk about the aldol condensation. So the today's reaction is we're going to condense or form a new CC bond between the benzaldehyde and the acetone molecule here. So we're going to use our acetone to form a bond. See, here's the acetone. It formed a new bond between this bond here and this bond. So it's forming a new CC bond to benzaldehyde, and we're losing water. So condensation means you kind of join two units together, and you lose a molecule of water or some other small molecule in the process. That's what condensation means. A condensation reaction. It's quite different than what condensation is, the physical process where you have a water vapor, you condense it back down, cool it back down to a liquid state. That's called condensation. But here it's called a condensation reaction. So the reaction is very different. Ironically, they both relate to water. Condensation here means you're just producing water. So this reaction, we're going to use a base to generate a reactive nucleophile with acetone here. And then our benzaldehyde is our electrophile. Notice it has no alpha carbons with hydrogens on it. Only acetone does. So this is our electrophile. So we call this a mixed aldol because one reagent is going to function as our nucleophile, and another reagent is going to function as our electrophile. So we don't get no mix and matching. So we could limit the complexity of the product mixture to just one molecule. So we're using two equivalents just so we get this molecule here, and we just don't get one equivalent where only half of the acetone molecule reacts. Okay, ethanol is our solvent, our organic solvent. So that's the only role it plays. It could play a role as a proton transfer agent, but that's pretty much it. Okay, so that's our reaction for today. So this is important because it features a formation of CC bond between two carbonyl groups, and usually this only works between two aldehydes, but it can work if the ketone is the nucleophile. Ketones are less reactive than aldehydes, so aldol condensation between two acetone molecules is very unlikely to happen. You need to use some tricks in the lab to get it to go to completion, but we're not going to talk about that. So in this reaction, only one partner has enolizable protons. What that means is it has alpha hydrogen atoms that can be deprotonated to form an enolate intermediate, and only acetone can do this. And benzaldehyde can't do that because it has the only alpha carbon it has is this one right here. Alpha is one away from the carbonyl carbon right here, and it has no proton, so we can't deprotonate it. Okay, so let's talk about the possibilities of the mechanisms in this reaction. So we all know that if we have an alcohol and an aldehyde or ketone, we can possibly get acetal formation. So it's an equilibrium between the free form and the hemiacetal form. Notice that you can't get acetal formation in basic conditions. That's not possible because you can't kick out O minus. So the only way we can do, the only thing that can really form is hemiacetal formation right here. So you might have learned that acid formation, the acid catalyst, acidic conditions, you can form acetals, but in basic conditions, you can't form acetals. You can only form hemiacetals. And that's why this reaction stops, because these are unstable and they just go backwards to acetone. And the base here can be, the proton source could be water. There's lots of water in the reaction because you're using aqueous hydroxide. But there's also a lot of ethanol, so it could be either one of these. Either one of these can act as the proton source here. Okay, so that's hemiacetal formation. We also have hydrate formation, so we can form a geminal diol using hydroxide. Hydroxide is a good nucleophile too, but as you notice that usually geminal diols are not very stable unless you have electron withdrawing groups on these carbon atoms. And since we don't have that, it tends to favor the acetone part, so the keto form instead of the geminal diol form. So it's favored this way just because it's more stable than having two OH groups bonded to the same carbon atom. Okay, so these are just giving you ideas of what can happen in the reaction. All right, so let's talk about the enolate formation. So thermodynamically speaking, this is the preferred intermediate because we're actually forming a resonance stabilized structure. And it turns out this intermediate is much more stable. It's much more reactive than the other intermediates. And over time, thermodynamically, it'll be the more stable intermediate to form because the other mechanisms, they can't really go anywhere. They just stop at that intermediate. And since it's unstable, it just wants to revert back. But this reactor intermediate can react with benzaldehyde to form a new carbon-carbon bond. So the process is we use our base, the protonate here, the alpha hydrogen, the hydrogen on the alpha carbon. We get our carb anion. And you see here, we could draw a resonance stabilized form of this carb anion, and we call this an enolate. We call it enolate because it's a hybrid between an alkene and an alcohol or alkoxide. So we call it enolate ion. If this is protonated, we call that an enol, E-N-O-L. So these are very common intermediates in organic chemistry for forming CC bonds, so they're very important. In theory, you could form an enolate ion from any carbonyl derivative, so ketone, aldehyde, except for formaldehyde, you can't do that one because it has no carbon atoms on the side. Amides, esters, you may have seen esters in class, 1,3 dicarbonyl compounds. What else? Carboxylic acids. And I think that's it. You usually don't see enolates from anhydrides because they break down easily, more easily, or acyl chlorides because they do weird stuff. But any carbonyl compound you can envision kind of doing this acid-base chemistry here. So this is our reactive intermediate. So if you have any questions about this mechanism, I recommend you ask them now because you have to reproduce this for the lab report and probably on the quiz where you'll probably be asked to talk about or do problems based on aldol condensation type chemistry here. Okay, so that's the enolate formation. Now we're going to go over the mechanism, the complete mechanism. All right, here's the mechanism. So I'm just going to go step by step. This first step we already covered. So we formed the enolate, produced water in the process. Okay, so since this is reactive, it's going to react with the electrophile it sees. So since it's in equilibrium, it can simply go backwards and get a proton and go back to the acetone. So that's in constant equilibrium. But what drives the reaction forward is the presence of benzaldehyde. So that's the forward reaction. So we attack the electrophile. Remember, benzaldehyde is electron withdrawn from the benzene ring, and the oxygen makes this carbon electropositive. So it's going to be attacked by this enolate. We push down electrons to reform the double bond, use the bond electrons from the alkene to attach the carbon bond at this carbon atom. Don't attach it here because that'll be a Texas carbon, so don't do that. So it'll attack this position, and we see here we form an intermediate alkoxide ion. So that alkoxide ion is unstable, and it'll just reprotonate from water to regenerate hydroxide. So here, this is what we call the aldol product, or aldol addition product. Sometimes you can stop at this product, but unfortunately for us, we can't because this next step actually drives the reaction's equilibrium forward so we can isolate the final product. So there are ways to isolate this, but usually you can't, it's hard to stop at this stage because the OH wants to leave as water or just leave as the molecule and be eliminated. And this is what happens in the next step. So we do the same process again, form a carb anion. Please show in your mechanisms, always show your resin structures. You'll lose points if you don't. So show the resin structure here. So this is I don't care what resin structure you use for the mechanism. I just like using the enolate because it's the more stable resin structure because it has a negative charge on oxygen. See here? So see here, we generate show the other resin structure here, conjugated to the alcohol. Now next, what drives this reaction forward is the ejection of water. So it's kind of entropy driven and heat driven. So it'll generate a lot of heat. Well, actually, you don't use heat, but I would assume that if you're generating water and hydroxide again, it'll generate a lot of heat. So I think it should be an exothermic reaction, and that's what pulled the reactions forward. So once you form this, it'll pull this reaction all the way forward, and eventually all of your starting materials will go to product because of the favored equilibrium process going forward. So we kick that out, move the double bond here, and kick off OH, and what we form is the alkene here. So we call this a alpha beta unsaturated ketone because it has an unsaturation at the alpha and beta positions. But I don't. That term you probably will have to know unless Dr. Levinson mentioned it. But it's alpha beta unsaturated ketone here. Then we generate OH minus and water again. And now since we have two equivalents of benzaldehyde, this thing happens twice. Okay, so what I want you to do on your post lab, you want to kind of pay attention here. So you're going to repeat this whole process, this whole series of steps twice for the mechanism problem. If you don't do it twice, however many points this is worth, you're going to lose half of it. So please draw the whole mechanism twice. One for this side, and then do the same series of steps for this CH3 group here, mimicking the same process here. Oops. Okay, so if you don't do that and you're kind of lazy, you're going to lose points. So my warning right now is make sure you do this mechanism twice. So don't simply write ×2 at the end. You won't get any points for that. Okay, that will not suffice. So I was instructed, to kind of emphasize this mechanism. It's going to be important. So you probably seen it in a lecture. You're going to see it again and again. Okay, so that's the Aldol condensation. So let's talk about the actual experiment. Okay, so why don't we make the hemiacetal? Okay, because the reaction is reversible. Oops, I was supposed to ask you that question. I'll make sure to ask you that the other questions and not simply answer it right away. It's because the reaction is reversible, and the hemiacetal is not really isolable, right? On the quiz they ask you, are hemiacetals, can they be isolated? And sometimes they can. Usually, cyclic hemiacetals can be isolated because there's a thermodynamic effect with forming a cyclic structure versus a linear one. So linear ones usually you can't because they're always favored for the ketone. But if you could form a 5 or 6 membered ring hemiacetal, those are favored to form based on just the ring size and what relative proximity of the OH group and the ketone or aldehyde group that are formed in the reaction. So usually rings are good, not so good for linear hemiacetals. Okay. So why do we react twice on acetone? Does anyone have any guesses? Is it all right? I'll wait for a few seconds. No one answers. I'll just move on because there's a lot more slides to get through. So why do we react twice on acetone? All right, no takers. All right. So because we have 2 alpha hydrogen atoms on the ketone, one on the right side, the CH3 groups, and one on the left side, the CH3 groups. Okay. So let's talk about the reaction. This reaction is actually pretty straightforward. It's too bad you can't run it in the lab. It's pretty cool. You actually isolate the solid. So here is our reaction setup. One solution, we have the sodium hydroxide and ethanol. And the other, we have the acetone and benzaldehyde. So we want to mix them separately so the enolate can form more easily. So you don't want to mix them all together at once because the enolate, it might be hard to form the enolate because you could form the acetone enolate, and then that will get deprotonated, and that will attack acetone itself or without benzaldehyde. So it's better to add them as a mixture rather than adding them one at a time. So we ensure that we form our reactive mixture and everything goes smoothly. Okay. All right. So why can't we mix sodium hydroxide and ethanol? Are there any guesses? All right, let me ask you this. What are the pKa's of like water and ethanol? Are they similar? Are they different? Are they really different? Right. So we use ethanol because we need organic solvent. But anyone have any ideas why we can mix it? No? All right. So let's go over it. we don't care about the ID of the base. We know one of these things are going to act as a base. So these pKa's are pretty similar. Sodium hydroxide is around like 14. Ethanol is like 15 or 16. So it doesn't matter what base we use. It's either going to be edoxide, ETO minus, or hydroxide, OH minus, that's going to act as our base. We don't care about these acting as nucleophiles because these aren't going to be the nucleophiles, as we saw. Those reactions forming the hydrate or the acetal, they're not going to be favored because they're highly reversible, and it's not favored towards the acetal, hemiacetal, or the geminal diol. So we don't have to worry about that here. Okay. So ignore these specs here. I couldn't find a good picture in ChemDraw that gave me a plain beaker. So that's too bad. But okay. So, all right. This is a good question. Why doesn't any reaction occur within this beaker with just acetone and benzaldehyde? So why doesn't any reaction occur? Does anyone have any guesses? All right. No takers. All right. So there's no base present, so no reaction can form. So if you just mix acetone and benzaldehyde, they'll just form a solution. They won't do anything. So really, they're pretty stable molecules. So you really need a base to kind of accelerate a reaction event. Okay. So how much of the organics do we add at first? So those of you everyone who took the pre-lab quiz probably read the manual, or maybe they didn't. So can anyone tell me how much of the organic mixture do we add first? I should just make these participation questions. Any ideas? I'll wait for like 10 seconds. Good, thank you, CC. Half. We don't want to add all at first because we want to get the reaction going. So we add half first, then half later. So we're going to add 1/2 of the solution. And usually with aldol condensations, you have to be careful because forming the enolate versus the enolate attacking itself can be tricky. So usually you do these reactions at low temp where you generate the enolate, then you slowly add like through a tube by vacuum or by using pressure. You add the electrophile slowly to the solution while it's gently stirring. So we do that to continuously generate the enolate, and once the enolate reacts with the added electrophile, it'll just repeat that process over and over. So chemistry is kind of like cooking. It's a very fine art. Everyone can do it, but not everyone's going to get the same result. Okay, thank you for answering that question. Let's go on. Reaction. Okay, let's talk about next step. Okay, so what temperature are we running the reaction at? The beauty of this reaction is you run it at a very normal temperature. So what temperature are we running the reaction at? Good, thanks, Laya. Room temperature, good. So that makes things a lot more simple. We don't have to chill anything, so it makes everything much more simplistic. So room temperature. All right. So it's important that we swirl the reaction like all the time when we're doing it. Does anyone know why? Or anyone have any idea why it's good to make sure everything is being swirled, the reaction mixture? So usually in chemistry, when you're doing a reaction, you either have a good, great answer, right? So you want to make sure everything's reacting completely, so everything's kind of having a chance to react. So we want a uniform mixture, or so that a uniform or a product can form completely from the reaction. So that's correct. So usually when you do chemical reactions, we have what we call a stir bar, a magnetic stir bar, and we use something called a stirrer to stir the reaction, so we don't have to do it manually. For example, if I have to monitor a reaction for 8 hours, I don't want to stand there and swirl it for 8 hours. I want to go do something else, or prepare my next experiment. So usually, to make reactions go as best as they can, get the best result, we have to stir it repeatedly and throughout the duration of the experiment. And that's why we use magnetic stirrers. So usually we have Teflon coated stir bars that are magnetic, and by using a stirrer, we could automatically stir it by itself. Of course, it uses power, but it's much more efficient than humans. Good, very good. Okay, so when do we add the second portion? So we want to add the good after 15 minutes. So we add it after 15 minutes. So we should see the mixture get turbid. That means the reaction is occurring, because I think your product is not very soluble in ethanol. So if it starts to become turbid, that means your reaction is working. So then after about 15 minutes, we're going to add the second portion, because we got our reaction to go. So we're just going to drive it to completion now, and we add it after 15 minutes. Okay. All right. So why do we rinse with ethanol? So once we transfer our flask, or transfer our stuff from so after we transfer our stuff to the filter, why do we rinse the flask with ethanol? Why not another solvent, like I don't know, acetone? Why not acetone? So why do we rinse our beaker with ethanol? Oh, sorry, this is not talking about filter. This is talking about when it's transferring the solution. So why do we rinse with ethanol? So these kind of questions, I don't know if people ever worked in labs, but these are questions you kind of ask yourself, because everything has a reason, right? We just don't do anything off the fly just because it's convenient. Sometimes that's the case, but usually not. Usually these experiments are well thought out, and you have to take into account these kind of circumstances. So I would just answer, since no one's answering. So we want to get all the reagents as much as possible in the flask. So if we use ethanol, we can bring all the stuff that's probably left over. When you transfer things, stuff kind of stick to the sides of the beaker. So we're going to use ethanol to kind of rinse it and get everything into our flask or our reaction. And since ethanol is our solvent, that's the best choice. We don't want to use more acetone. We don't want to use more benzaldehyde, because those are our reactants and we can affect the reaction rate. So we don't want to play with those variables. Okay, so that's the solvent. Oops. All right, I already answered this question. So we react it for a total of 45 minutes. Can the reaction go longer? Sure, but that's not necessary here. We're just trying to get some product and isolate it. So we're going to react it for 45 minutes. Okay, so let's talk about workup. Workup is pretty simple. What we do is we collect by suction filtration again. So we saw that last time. Hopefully everyone remembers what that looks like and how it proceeds. All right, so let's ask this question. What is being removed in the filtrate? So what is in the filtrate that we don't want? So we got our solid, right? Our turbid solid. We have a mixture. We want to isolate the solid from the filter, the liquid part. So what's in the liquid part? Anyone have any ideas? Any ideas? All right. So assuming all the benzaldehyde, oh yes, water, ethanol. What else? What else was in the reaction? There's water. Yeah, ethanol. All right. What came with the water? Something else that we don't want in our product. So there's ethanol, but like what else did we use to get the reaction going? Any ideas? All right, so first we formed a solution of ethanol and what was the other thing that was part of that mixture? Ethanol and anyone? Yes, great. Thank you. Right. So we had water, ethanol, and sodium hydroxide. Very good. So we're going to we want to remove this because we don't want the product to be basic. So we want to remove the sodium hydroxide and the ethanol. We want it to be dry. Okay, so we're going to discard the filter into the ethanol sodium hydroxide waste. So if we were to do this experiment, I would direct you to draw it here. Okay. So, but you're not done yet. You need to reattach the Buchner flask and you need to wash your product with another solvent. Okay. So why do we wash the product with DI water? Any ideas? Like what might be stuck on the product that we need to use DI water? And why should it be cold? Good. Yes. Great answer. Right. So we don't want any sodium hydroxide on there because that would contaminate it and it'll be impure. So we want to get rid of the sodium hydroxide, right? So remove the traces of sodium hydroxide that may have gone on it during filtration. Okay. So then we're going to talk about the waste. So in this case, once we're done filtering, right, what is our waste? Do we want the liquid part or do we want the solid part? And ask yourself this question: how and why do we test the waste before disposal? Actually, I'll talk about that. But so what part is the waste in this case? Is our filtrate our waste, or is our solid our waste? Any guesses? Don't worry, no guess is wrong. As an educational guess. Liquid waste. Good. Right. Solid's not waste. Thanks, Roy. Liquid is the waste. So the thing about here, since we're washing with water, we don't need to we can actually dispose of the water in the sink, but first we have to test it. So why do we test it? Oh, it's because it might be basic, and we don't want to dump basic solutions down the drain, especially since sodium hydroxide is a strong base. So what we do is, so to ensure that the water that we use is neutralized in the filtrate, we're going to test the pH with pH paper. Now, if it's basic, we're going to add citric acid and make sure it's neutralized. Then, once we have a neutralized solution, it'll just be water and sodium citrate, which is very, environmentally friendly. So we don't have to worry about any environmental concerns. So we could dump that down the drain. So if there's any way you can reduce waste into non-toxic byproducts, we, of course, implement it in experiments. We do not want to generate toxic gases or toxic byproducts. Because with doing chemistry, we have a certain responsibility to keep the environment safe. So we're not destroying it. Okay, so that's how we limit waste generation. Okay, so we're all right, guys. We're almost near the end, so stay with me for a little bit longer. So we're learning a new technique today called recrystallization. So filtering might remove the liquid from the solid phase of your mixture. However, if you have an impurity that is solid, you can't remove it with filtration. it'll be present in the solid. So we have to do something else, and that's called recrystallization. So recrystallization is that's our technique we're going to be focusing on today, our purification techniques. So purification techniques, they're not really chemistry, it's more like physics, how you're trying to manipulate properties to remove something from something else. So that's more of a physical change, not like a chemical change. Okay, so I've talked about recrystallization. This is the picture. Kudos to this person on Wikipedia. So if you go on Wikipedia, they have very useful images. Okay, so here is a breakdown of what's happening. So we have our crude solid here. It's about, like whitish yellow. We're going to add solvent. So we're going to add a minimum of solvent. So this is what we do. First, we add solvent to our compound. In this case, the compound now will be won't probably dissolve. So we want to choose a solvent that won't dissolve the compound at room temperature, because if it dissolves at room temperature, there's no way you're going to isolate it without evaporating the solvent. Next, we heat the solvent to make sure everything dissolves, gives it a uniform solution, and we say it's saturated because now it's saturated with the compound. Okay, then next we allow it, after we heat it to enough temperature where everything's dissolved, we're going to let it cool down to room temperature slowly in ice to give, and then what happens is the impurity will stay in solution, but your product will precipitate out as nice crystals. So that's how we recrystallize something. We are removing the impurities by dissolving the impurities in a solvent that can dissolve it. So see here, after here, the saturated solution becomes less saturated because at lower temperatures, our compound won't be as soluble and it will precipitate out. And this technique takes advantage of the fact that our impurity is soluble in our chosen solvent at all temperatures, but our product is only soluble in the solvent at high temperatures. So that means our product will precipitate out at the lower temperatures here. That's the technique we're using today. So they use this a lot, especially in pharmaceuticals, to purify things, because you want to be able to purify things using techniques that aren't like solvent intensive. So this is a great way to do that. All right, so let's talk about the next thing. So what we're going to do is we're going to use ethanol. So we're going to use ethanol as our solvent, because we noticed that in the reaction, it doesn't dissolve it at a low temperature. It crashes out our product. So we can use ethanol as our solvent. Okay. So let me ask you, how much solvent should we use when we're doing recrystallization? So remember, your product may have some solubility in ethanol. So do you want to use a lot of solvent or a little solvent? Any ideas? Right, great. So we want to use a little solvent, because if we use a lot of solvent, it turns out it might not work as well, and it may dissolve your product if you use too much, even though it has low solubility. Okay, so we want to use as little solvent as possible. So we use hot solvent. We want to use hot solvent to dissolve the impurities and our product. So we want to make sure our impurities dissolve, so we remove them from the solid. So that's the technique here. We're removing the impurities based on a solvent's solubility properties. Okay. So how do you know when there's enough solvent or too much? Some students may ask this, like, Oh, Andrew, how much solvent do I add? Well, my advice is you always start off with a little, then try to agitate, make sure try to get things to dissolve first. And if you need more, add a little more, but don't add too much. So don't add too much at first. That can cause you to lose product and your yield will go down. So the name of crystallization, your crude yield will always be higher than your pure yield because the pure yield, you lost some impurities, so the mass will go down. So common errors are you add too much solvent, then you don't get crystals. Then there's another situation where you don't get crystals, and then there's a little tip you can use where you scratch the sides of your beaker. So what that does, it creates irregularities on the surface of the glass, and this causes an event called seed crystal, or crystals will begin to gather on the sites of the glass. We call those nucleation sites where the crystals can grow. So that's how crystal growing work. Crystallography is very tricky. I tried growing crystal before, spent months doing it, got nothing. So it's an art. But usually, when we're doing chemistry, sometimes a crystal structure is the best way to provide evidence that you made something. And usually you need that when trying to to convince the public that what you made is what you say. So usually a crystal structure and solving it is direct evidence for that. So crystallization, crystallography, very, very important subject. Okay, so that's crystallization process. I think that is it for the lab procedure. So let's go on to a few more slides. I'll give you the data you'll need for this experiment. So it's a shame that someone left because they won't have the data, but I'll send them the slides, so it's okay. Okay, so your analysis, we're going to analyze the product by melting point. Check out the video for the value to put in your lab report. So once you get to the video, on the next page where it says, I think to analysis, after the melting point video, there'll be a results page that has the melting point results. So I want you to take those values and average them and put that average value in your lab report. So do that. So here's the data to use for the calculations. So you're going to be given the mass of acetone and benzaldehyde. I want you to convert this to volume and moles. So make sure you copy this down before you leave. And here's the data for the product. So remember, product, the isolated yield is the full mass of the vial plus product minus the empty vial and the rest of the stuff that goes with the vial. And the difference is your isolated or actual yield of dibenzalacetone. Okay. I believe that is the last slide. Let me just make sure. Yes. Okay. Are there any questions? All right, I'll leave the slide up for a few minutes, but there's no questions, everyone. That's it. Thanks, everyone who answered my questions. Please keep doing that. And if there's nothing else, you have no questions, I'll see you next week. Unfortunately, no, there's no office hours on Monday. Please go to another TA's office hours, or if you can wait, go to mine on Thursday, or just ask. You can email me too. You're welcome. Have a great weekend, everyone.